In order to keep to time as much as possible, I'm really pleased to be able to introduce Emily Howerton, who's going to be talking to us first about what we can evaluate from her experience in detectives. Thank you.
Hi everyone. I want to start by thanking the organizers for being here. It's been a really wonderful week so far. I've been learning a lot and having a lot of great conversations. Before I start, I also want to thank Justin and Cecile for all of their help on this work. We've really been thinking about this problem together. And the question that I want to pose to the group today is, what can we learn from evaluating scenario projections? We've heard in the last session alone a lot about the scenario projections that were used during the pandemic. We made them in the US as part of the US Scenario Modeling Hub. And we make these projections all the time with our models, right? We say, what would happen if there was no vaccination? What would happen if there was lots of vaccination? And as we heard so elegantly from Seb on Monday, evaluating these scenario projections is really important. One, for improving the quality of our models, but also for convincing policymakers and the public that we're worth believing. So in contrast to forecasts, which there's a large literature for evaluating these unconditional forecasts of the future, and a lot of that literature kind of boils down to some comparison of the forecast that was made and the observation that eventually materialized. But in the case of scenario projections, evaluation is a bit more difficult. We still have these observations that we can use to ground our evaluation, but this explicit comparison between the projection that was made and the observation that eventually materialized, it's more complicated to interpret. And the reason that it's more complicated to interpret is that there's actually two different reasons we might see differences between projections and observations. And so to tell you a bit more about, these are very intuitive reasons, but to tell you a bit more about them, I want to go with this very simple characterization of the kinds of scenario projections we make in the US. So you can imagine we have a low vaccination scenario and a high vaccination scenario, and we're making projections for something that we care about. Here, let's say it's cumulative hospitalizations, right? So one model gives us two projections. But the fundamental problem in scenario evaluation is that the observation that eventually materializes of how many hospitalizations actually happened, it comes from a world that doesn't match either of the scenarios that we modeled, right? So this is one reason that observations and projections may differ. But you could imagine a case where we modeled the perfect scenario. This is a hypothetical case, but you could imagine that hypothetical scenario. And even in this case, if scenario and reality match perfectly, there's still the possibility that the models themselves are imperfect or miscalibrated in some way. So let me give you an example from the US Scenario Modeling Hub just to show you what I mean. So on the left-hand side is a vaccine uptake scenario that we modeled in early 2021. And on the right-hand side is a projection from one model for this particular scenario. Now what we can do is go back and independently evaluate the scenario assumption itself. So the black line shows you data on observed vaccine uptake in the US. And this gray area is what I mean by scenario deviation. But this is quite a unique example because projection or scenario and reality are very close together for these first few weeks. This hardly ever happens, but luckily it did once, so I can show you. And when we look at the observations for incident hospitalizations compared to the projections, even in this first few weeks, we see differences. So this is what I mean by the models themselves can be miscalibrated. And really what we think is happening is when we see error between projection and observation, it's some complex combination of the scenario being wrong and the model being wrong. Many of the questions we want to ask, though, are about the calibration of the models themselves. We want to take out this scenario deviation error. And ideally, if we knew something about this function f, we could take the error between projection and observation, we could measure the scenario deviation, kind of like I showed you before, and then use the properties of f to infer what m would be. But unfortunately, this f thing is relatively unknown. So what we did as a first step is to make some simplifying assumptions. And the simplifying assumption that we made is that when the scenario is close to reality, the error that we observe is a pretty good proxy for the calibration of the models. So we basically take the 4 scenarios that we have in US Scenario Modeling Hub, and we subset only to those that are kind of still plausible in this retrospective evaluation of the scenario assumptions. So what I'm going to do is I'm going to show you some results from this approximation analysis, and then I'm going to tell you about a method we've been working on to get at this ideal approach. Okay, so our analysis using that approximation method was for the first 16 rounds of COVID-19 projections in the US. Each round on this figure is a different color, and a round basically just means a different set of projections for 4 scenarios. So that's why up here you have 4 lines of the same color. The topics of our scenarios kind of changed as the main questions of the pandemic were evolving. So early we focused on vaccination and NPIs, and then later we focused on the emergence of new variants and waning immunity. Usually our projections were 26 weeks into the future, sometimes shorter, sometimes longer, but these kind of longer range scenario projections is what we're making. And one of the key features of the Scenario Modeling Hub in the US is that we have projections for the exact same scenarios from 4 to 9 independent modeling teams from different universities, and then we ensemble those. So these predictions up here are the ensemble. So using that approximation approach, we evaluated the scenario assumptions themselves, and we picked only those that were still plausible retrospectively. And one of the questions we wanted to ask was this all worth it? Does the ensemble give us the benefits that we think it should? So on the horizontal axis here, you have each of the individual models in the ensemble, and then on the vertical axis, you have the rounds of Scenario Hub projections. The white space is just because not every model submitted to every round. So we used weighted interval score. This is a pretty standard metric in forecast evaluation. If you're not familiar with it, the details aren't that important. But essentially, we've relativized it here. So anything around 1 in the white color is about average performance, and anything in the green color, less than 1 is better than average. So the first kind of most obvious conclusion from this analysis is this clear performance benefit that we get from ensembling multiple models. And this has been found in many other fields. And I think one of the other really important conclusions from this work is that if I highlight the individual model that performs best in each round, you can see how inconsistent it is. So if we were to have picked just one of these models and relied on that for decision making, we might have made some really big mistakes. So not only do we have performance improvements, but we have this consistency and this reliability that becomes super useful when we're using this information in real time. But you might be wondering, okay, these results are based only on the most plausible scenarios. In order for our projections to be most useful, we kind of want to know that all of the scenario projections are well calibrated, even for the scenarios that didn't actually happen. So to test whether or not we kind of have this well-calibrated scenarios more generally, we did a second analysis where we evaluated all scenario projections regardless of the plausibility of the scenario. So each dot here for a round is going to be the performance of the ensemble projections for each scenario, and the orange highlighted ones are going to be those that the projections that come from scenarios that are still plausible retrospectively. So in round 1, we see the pattern that we would expect. We're using weighted interval score here, so lower is better. So the projections that were closest to observations were also those that were from scenarios that actually were close to what happened. But if we look across all of the rounds, we see that this pattern actually doesn't really hold much at all. So if you look at round 4, for example, we have a couple projections that are doing quite well, but they're from scenarios, they're based on scenarios that are not even close to what actually happened in the world. So this we're kind of getting the right answer, but it's for the wrong reason. And so this motivates the importance of really teasing apart the error that's driven by the scenario assumption itself and the error that's driven by the calibration of the models. So we've been working on a new method to kind of do this, and to explain to you the motivation and the logic behind this method, I want to go back to this simple sketch. So remember, we have our 2 projections here, we have our observation that comes from a different world, and then we have this hypothetical kind of perfect scenario projection. You could imagine we might get this by rerunning the models retrospectively with the new scenario value, or even just kind of doing some interpolation along this scenario axis. But also theoretically, there's 2 kind of true values at each of the scenarios that we modeled. How many hospitalizations would there have been if we had the low vaccination scenario realized? And the thing we're actually most interested in is how well calibrated is this projection, right? How much error is there between this hypothetical true value that we will never observe and the projection that we made? But given that we'll never observe this, we decided to go with something that we could measure, right? And that's the error between the projection in the sort of perfect scenario and the observation that actually happened. But this error alone can only tell us so much. So what we propose to do is use variation that emerges across projection. So in the US, for example, but I think this happens in a lot of places, we have some locations with low vaccine uptake rates, and we have some locations with high vaccine uptake rates. And so what we propose to do is plot this error that we can measure across the scenario axis and then regress that, right? So we're trying to estimate the kind of error distribution across this scenario axis. And then what we can do is a bit of extrapolation to what would the error distribution have been for each of the scenarios itself. We're doing some simulation experiments to test this and see when it breaks, see when it works, which are in progress now. And so very happy to hear your thoughts on this method. But I think it's a really exciting potential opportunity to evaluate all of the scenario projections that we make all the time, and also potentially in other fields like climate or economics where they do the same type of thing. I will quickly put in a plug. Justin Lessler, tomorrow morning, first talk, will discuss scenario evaluation ideas from a different perspective, the policy perspective, how our projections are used to inform policy. So please make sure you get here at 10 with your coffee or tea, whatever you use, and hear what Justin has to say. And I'll finish by thanking all of the members of the US Scenario Modeling Hub, Cecile and Justin, and also my postdoc advisors, Jess and Brian Grenfell at Princeton, for their support for being here and in general. Thanks for listening.
No questions. Lloyd.
I was just wondering what's the reasoning behind expecting the calibration error to be linear in the, along the scenario?
That's a good question. So I don't think we do. You could imagine we could fit something more flexible to that distribution. In our first simulation experiments, we were having a bit of trouble with that, but I don't think the linear assumption is necessary for this method to work. Yeah, but the shape of that is hard to know, right? Yeah.
Jumpy.
Just a quick one. I noticed that you treated these scenario projections as one value, but most come with a kind of confidence bands of things. If you evaluate according to did reality fall within a confidence band, does your evaluation change?
Yeah, so that simple sketch I just used point estimates, but in Scenario Modeling Hub, we have full probabilistic predictions. And so the theory we're developing would be extended for probability distributions, and that weighted interval score that I showed accounts for, it kind of evaluates the calibration of that probabilistic prediction. So I oversimplified, you're exactly right. We need to make sure we have error, right? Yeah, thanks. Yeah.
Could you take the model and go back and run it with the data that sort of subsequently came in? So you're then running the model on what turned out to be exactly the correct scenario, so that you then get rid of the scenario error and you just get the model error.
Yeah, so that's exactly right. I don't know if you remember in the sketch, there was that open white point. That's one way that we would get that projection. But the limitation with that is it only tells us the calibration of the model in the world that actually unfolded. But you could imagine a counterfactual scenario with no vaccination at all. And it's not clear that the calibration in this current world tells us much of anything about the calibration in the counterfactual world. Yeah.
So maybe time for one more. Thomas.
So I think this is incredibly useful. We got in the most dreadful trouble for this in the UK. I think with some people just deliberately misinterpreting what we meant by a scenario. But I think that obviously you're doing what you can do here and talk about vaccine. That's something you can measure. The issue is, what if your model contains some kind of intensity of NPI, which no one was ever able to. So there's this like Oxford database of their subjective evaluation of how intense the NPI was, but that never really correlated with anything. So have you thought about how to do it for something like that? Because that was often much more uncertain than vaccine coverage.
Yeah, that's exactly right. So I think one thing that will come out of this is kind of a set of constraints or guidelines for how you design scenario projections if you want them to be evaluable. Maybe NPIs is something that we can evaluate. But you can also imagine kind of in the cases where we can, decomposing the error for policymakers or someone into this error that's driven by scenario and the error that's driven by the models. But sometimes we're going to have to make projections for things that we can't measure, and we're going to just have to come to terms with that. But maybe if we can measure in other domains, we can convince people of the kind of reliability of our models more generally. Yeah. Also, I think some of Justin's thoughts on tomorrow will maybe get at that too. Yeah.
Okay, great. Thanks so much, Emily, again.